It's my pleasure to speak at the ECS Student Chapter Energy Seminar Series. The topic today will focus on what I feel are some very important types of measurements that can help in the mechanistic understanding of your electrochemical systems, such as batteries, fuel cells, and solar cells. So the title of the talk, succinctly, is Think Globally, Measure Locally, and trying to convey that the big picture that you want to get mechanistically from your devices and your materials need fundamental measurements that are always ultimately at the fundamental scale going to be at the atomic level. And so when I say locally, first I mean locally at the scale of individual atoms and their atomic neighborhoods. The second sense in which I use the word locally is more of the physical sense of where you do your experiments. And so it's a kind of play on words with the word local here. And the second sense of the word local is trying to convey the idea that that there is often the ability to measure atomic level local structure of the type that is most interesting um, is not something that is accessible locally, and you need to go to a very centralized high-end facility in order to conduct those experiments. So one type of local measurement is at odds with another type of local measurement. So I will try to basically speak to that and say how, if we think of that as a challenge, we can essentially try to mediate that challenge by developing local access to local measurements. Let me go to an acknowledgement of my group and also bring about a laser pointer. So this is my current research group. Just a recent picture of my research group. Many of the people here are associated with some of the topics that I'll be discussing. And I want to specifically point out Abhiram Krishnan and Ian Slagle sitting next to each other because they are the ones who are running and maintaining this one of these local instruments that I'll be referring to, and that allows us to do the kind of spectroscopy that normally would be only possible at a external facility. But several other people's research work, for example, Ken's research work here, Bhavesh's work, Sumaya's work, are all also connected to this instrument. So let me start with just a simple example of a type of system. Here we're looking at, this is a global picture of a lot of things, so I'm going to try and walk you through what this is about. So from the suggestion of the title of the slide, it is what the point I'm trying to make here is that it is important to have the ability to track the chemical role of each of the constituent elements in your material while it is under operating conditions, and do so non-destructively. So in other words, what is often referred to as an operando experiment, if that can be done, and you can still, while this reaction is happening, you can still follow the role of each of the constituent elements individually, that would essentially give you a big headway towards understanding how these processes work and how your system works. So here's an example of a nickel cobalt based cathode material in a battery. And what we are looking at in the x-axis is what is called the state of charge. And the state of charge is essentially the extent to which the battery has been charged. And what we're seeing here is that it is the state of charge is going all the way to 100%, and then it's reverting back to 0%. In other words, you're charging and then discharging the battery. On the y-axis, we see what is being referred to as an energy shift. So I'll come back to that in a second. But without even understanding what the energy shift here refers to, what we can see here in this picture is that we have two separate behaviors. One, which seems to be the behavior of the cobalt species. So would be this track here, and a separate track for the nickel species over here. So this is a very old example of the paper that a paper from 2 decades ago that did this kind of work to show the role of each of the constituent elements. This particular work is actually not done using an operando experiment, but rather with a series of ex situ measurements. That is, making batteries, charging them to a certain state of charge, disassembling the battery, and then doing the measurements. So the question now is, what kind of measurement is this? Whatever this measurement is, it seems to be quite sensitive to the chemical state of the element and be able to do these kind of measurements with separate information from each of the elements. The element that's missing, or two of the elements that are missing here, are in the overall cathode is lithium, which is obviously part of this lithium-ion battery cathode, and the other is oxygen. So lithium is it's the trigger in this case. The lithium is in fact being extracted, and it is safe to assume that lithium itself is in +1 oxidation state the entire time in the cathode material. Whatever lithium remains is always at +1 oxidation state, nominally speaking. But the oxygen information, one can assume that it is staying at oxygen 2-, but maybe it isn't. And that is missing from here. So one of the challenges one might say as well, what about oxygen? Isn't oxygen participating in the redox? So the question I still leave suspended for the moment is, what kind of measurement can give us this type of information? Let's look at another example now. So here we will, seems to be frozen. Okay. Before we get to the example, I just wanted to highlight that the details of the kind of measurements that I've just talked about can be found in this paper recently published, talking about how we can use lab scale X-ray emission spectroscopy together with X-ray absorption spectroscopy. So I'm kind of giving the answer away from the previous slide to monitor the redox process in lithium-ion batteries under operating conditions. And it follows from earlier work. My group is not the only group that has been doing this. This has been done by many others, but not at the lab scale, but at these external facilities. And at these external centralized facilities, such as synchrotron facilities, a lot of this kind of work has been done in the past. This is just an example from my group in the past. And that was with the so-called nickel manganese cobalt oxide based cathode materials, or NMC. So here's a different example. So now we're stepping away from batteries, and we're looking at what would be a catalyst for a fuel cell. So the question here is, what is a local measurement that we need there? So here in this particular case, we were doing a study of the atomic structure of platinum atoms as they are grown as a film on top of graphene. So the fact that it was growing on top of a film is something that we intuited from several other methods, but the first time that we actually were able to image this and show it directly was with the with this electron microscopy image that you see on the left. And once you have these kind of images, you can do a lot of analysis. You can actually see how the platinum atoms are templated on the graphene sheet, and you can do an analysis of how the registry happens between them. And so the point of this paper that this study came out in was to show that there was epitaxy between the platinum atoms and the graphene. But I want to point out to something else in the title here of this slide, and that is spatially averaged atomic local structure. What you're looking at here is not really spatially averaged. If you look at the scale bar here, it's 1 nanometer. So for a sample that is several millimeters across, 1 nanometer is an extremely local example of what may be happening in the material. In other words, there could be potentially all kinds of other things that are happening in other regions. And it just so happened that your microscopy experiment picked up on one of the phenomena that were happening, but not necessarily at the exclusion of other phenomena that were also happening at other locations. So microscopy type of work of this type is very, very intuitive because it gives us a picture, a real picture that we can use. However, this type of measurement, by the very fact that it's extremely local, we're looking at individual atoms, means that we are not necessarily talking about a global average of what's happening, right? And so in order to go from this to a global average, you would need to collect many such images and then do some statistics on that and make a further conclusions based on what's actually happening in the entire material. Now, of course, you can get around this by deduction and other analytical approaches where you can make the argument that, well, we really expect only one type of phenomenon to be happening, and this is it. This is representative. And so you can get around that. However, if you really want to be sure about what's happening in a global way, what you want is a method to get local atomic structure, but averaged over uh, many microns or millimeters of your material at the same time. So in other words, you would want to use a method which um, is designed to be spatially averaged at the macro scale. However, that same method gives you information that is extremely local, that is atomic scale. So atomic scale information, but spatially averaged over macroscopic scale. And that's where this technique that I'm kind of alluding to using X-ray methods comes in. Here, you're getting, again, atomic level information, which is specific to the type of element that we are focused on, but it is globally averaged over the size of the sample. So here, it's not the same kind of thing. You're not looking at an image anymore, but you're looking at a statistical representation of the kind of information that is embedded in the image on the left here. And what is that? It's the so-called radial distribution function. It is the probability of finding an atom at a particular distance. So if you're able to find an atom at a particular distance, you can organize that histogram, and that histogram now tells you what is going on in your material on average. So here, particularly, we're looking at platinum on graphene. So the atom around which we're focused on is the platinum atom. And so we're looking at these peaks here, and these peaks then represent the nearest neighbor and then the second nearest neighbor around platinum and so on. So what's the point of this distribution? The point here is that when we compare our atomically thin platinum on the graphene to bulk platinum, that is platinum foil, which is in black here, you can see that there is a compression. That is, the first nearest neighbor is at a shorter distance in the case of this atomically thin metal film compared to the bulk. This compression is real. You can see that the average, which is giving you a distribution here, the average position is now shifted down compared to the average position in the platinum foil. So here you do not have to worry about, well, is my information coming from this region of the sample or that region of the sample. It's actually averaged over the entire sample. And on average, we can now say that the platinum atoms are closer to each other by virtue of the fact that they have an epitaxial relationship with the graphene. So just to put a punctuation on this slide here, this kind of work was done prior to this kind of work in our lab. In other words, we understood already that there was epitaxy going on, because that's the only way we could explain the compression of the platinum-platinum bond distance before we had a visual proof of that. So I'm not saying that one is better necessarily better than the other, but they work very well complementarily. Okay, so another flavor of this local information is local in the terms of the atomic neighborhood, but spatially averaged. All right, so how is this type of information obtained? So I kind of gave it away earlier, but the way you can get at a lot of this information is by triggering the specific atoms that you're interested in to give you that information. And so the way to trigger the specific types of atoms is to basically knock out their core electrons and then use that core electron being knocked out directly, which would give you something like a photo emission spectroscopy, XPS, or look at the process by which the photon had to be absorbed in order for that electron to be pushed out. That's the X-ray absorption spectroscopy. Or the following event where the core hole that is left behind is then filled by another electron cascading down. And in that process of cascading down, a characteristic X-ray emission is released by that same atom. And so that X-ray emission now becomes a characteristic signal. All of these techniques carry chemical information. That is, the details of what type of chemical bonds are around that particular type of atom. Okay, so that's where the chemical information comes from. X-ray absorption is the unique one among these core hole spectroscopies, in that it also gives you atomic structure. X-ray emission gives you some details of the spin distribution that is harder to obtain from the other experiments. But the only technique here that gives you a very direct way of looking at the atomic structure is the X-ray absorption technique. So combination of X-ray absorption and X-ray emission is actually quite powerful. But the other part of this, the reason I'm only highlighting absorption and emission rather than also, let's say, X-ray photoelectron spectroscopy, XPS, is because these two techniques, XAS and XES, are X-ray photon in, X-ray photon out type of techniques. In other words, the penetrative power of the X-rays is something that we can benefit from. And so here, in many cases, we can actually design reaction cells where we can observe the reaction in real time, because the X-rays are able to penetrate into the cell through windows, observe what's happening, and the signal information comes out, obviously slightly attenuated, but still sufficient in order to give us the information. The same thing is much harder to do with photoelectron spectroscopy, although a lot of advancement has happened in near ambient pressure or ambient pressure level XPS. And I should say at this point that one of the new developments that's coming to Georgia Tech is that we are acquiring a near ambient pressure XPS system that will be primarily focused on the research of Professor Radcliffe, who's just joined us recently, but will be a user facility for others as well. So that third core hole method, XPS, is also potentially going to move us in the direction of in situ and operando type of experiments, albeit with a lot more challenges because of the fact that electrons are the signal and electrons don't travel very far. So let's take a moment to go through some description of X-ray absorption and X-ray emission, so that those of you who are not familiar with these techniques can get an idea. Quite simply, both of these, as I said, are core hole methods, and the core hole is generated by an external X-ray source to begin with. So then X-ray from the outside is coming in, gets and has to have the threshold energy to knock out a core electron. And once that happens, you're left behind. What you're left behind with is a core hole, and that's why this is called a core hole method. The electron that is released has several options depending on the amount of energy it has. If it has just enough energy to cross the Fermi level and fill one of the unoccupied states, then it is basically going to give you information about the densities of the unoccupied states, because the transition matrix, that is the probability by which this electron gets promoted to these empty states, depends on, or is directly proportional to, the densities of these final states. It's also proportional to other things, so one has to be wary of that. But the fact that it is proportional to the densities of the final states means that we can use this as an analytical tool to measure the chemical state of the element in question. Now, that core hole that's left behind by the absorption process is a very short-lived core hole. In the order of femtoseconds. So in that time period, another electron will try to come in and quench that core hole, because otherwise the atom is in a highly unstable excited state, and the quenching process goes some ways to returning the atom back towards the ground state. So anyway, that electron coming down will come from another characteristic level within the atom, which means that the energy difference between where it comes from and where it ends up, now that difference becomes a characteristic emission X-ray photon. So one electron dropping down releases one photon. So there's that one-to-one correspondence there. And that photon carries the information about the atom. Not only that, but also about the details of the chemical bonding and the type of ligand that the atom may have around it. But to put it in terms of electronic structure, simply X-ray emission is essentially giving you the occupied states, densities of occupied states. The X-ray absorption is giving you the densities of the unoccupied states. So they are complementary to each other in that sense. Looking at X-ray absorption in a bit more detail, here's what it looks like. The X-ray absorption spectrum will essentially be measuring how the X-rays are absorbed by your material. And so if you plot that on a normalized scale, what you'd expect to see is that not much is happening until you reach that threshold energy where the coral electron is released, and then you have all this information that is above the so-called edge. And so the edge is basically the energy required to reach the Fermi level for a core electron. And then the near edge region is basically giving you the details of that, the unoccupied densities of state. And then the extended region here, the so-called XAFs, is giving you the local atomic structure. So let's look at that XAFs part a bit closely. Why do we even have that? To say it simply, we have it because the electron, once it's released and once it's past the conduction band and is within the vacuum of the atom of the material, is now a free electron wave. Now that free electron wave, depending on its energy, will have a specific wavelength. This is the de Broglie principle. So that electron wave was now, you can imagine, going out and scattering back from a neighbor and returning. Fraction of that then returns back to the original atom, right? But the separation between these fringes, which corresponds to the wavelength of the electron, depends on the energy of that electron. So if the electron energy is higher, the wavelengths are narrower. So here are 2 points, this point here and that point there in energy. At this point here, the free electron has more energy, therefore shorter wavelength, and you can see that the fringes are narrower. And here it has less energy, therefore larger wavelength, and so the fringes are more separated. So what does that do? Well, when we're scanning in energy, then what we're doing is essentially we're changing the wavelength of the electron, but our structure is the same structure around. So it's essentially we're getting a picture of what's going on around the atom that created that electron in the first place. We're getting a picture of that atom over and over again with phase information. You see, the returning wave can either be in phase or out of phase with the absorbing atom or anything in between. So the fact that the returning wave oscillates between being in phase and out of phase and in phase and out of phase over and over again is the reason why we get these oscillations here. So in other words, we're getting multiple snapshots of pictures of the structure around the atom, and the larger this range of information we capture, the more clear that picture becomes, right? So the interesting thing here is that we have atomic structure embedded in the absorption spectrum, but it requires you to scan over a wide energy range in order to get a clear picture of that atomic structure. So this is uh, a challenge of the extended fine structure measurement, is that it necessarily is a wider band of information, and therefore often that also means that it takes longer to measure. X-ray emission is I've described what it is before, but even though it describes the energy level difference between two electronic levels, which are well defined, and that difference should essentially shift in tandem with each other when the chemistry of the atom changes. The very fact that there are different energy levels means that the outer electrons and the deeper core electrons don't shift the same amount due to the different levels of screening that they have to the different charges involved. And so what that means is that even though they move in tandem, that slight difference between that movement is enough for us to pick up chemical state information. That is a slight information difference. So we have actually a lot of choices of the type of emissions that we can use. And the most intense ones are the so-called alpha emissions, and followed by the beta emissions. And within the beta, there's an even smaller subset of beta that is the lowest cross section, but carries a lot of very interesting information. And that would be from the valence electrons down to the core, the so-called valence to core emissions. All right, so chemical sensitivity goes up as you go from left to right, but the intensity, the cross section, is higher when you go from the right to left. So, as promised, this is still chemically sensitive. So here's example of manganese 2+, 4+, and 7+, and you can see that we get that information from all three types of emissions in the K family. So now I'm going to get to the question of what is the locality part of this. So why is it that there's a challenge to doing these kind of measurements locally? And the reason is, as I suggested for X-ray absorption, you need an energy range over which you're going to scan. For X-ray emissions, this is not necessarily it's not a necessary condition. However, for X-ray emission, if you want to be close to the energy that triggers the core hole process to begin with, that gives you a much higher cross section. And so the ability to move in energy and select the energy at which you trigger that emission process makes X-ray emission much more attractive if you have a broad X-ray source. So broad energy source. So the broad energy X-ray source, where the energy the intensity of the X-rays is also high and fairly flat across that energy range, is a requirement, or it has been historically a requirement for these type of techniques. And so these kinds of techniques have been resorted to, these kind of large facilities that generate X-rays by phenomena that are difficult to replicate and at a lab scale. And you can see the footprint of these so-called synchrotron facilities are, in the size of city blocks. They're very large. So this is the NSLS-2, National Synchrotron Light Source 2 at Brookhaven National Lab. The one in the middle is the ESRF, I believe, and the one on the right is ESRF is in Europe, and the one on the right is the Shanghai synchrotron source. So three different parts of the world, but you can see from the aerial view that they're quite large facilities. So these require huge capital investments, and so it's not something that you can decide to bring to your neighborhood in the next few years. It's not going to happen that quickly. So what can you do? You can either go to these facilities to do these experiments, or you can try to adapt these type of experiments to your lab. So that's what I will be speaking of next. So these type of synchrotron facilities that I just pointed to within the US is also sparse. I mean, you have them, but they're located at different locations here marked. And you can see that in Georgia, we are very far from the nearest synchrotrons. Um, so I affectionately call this the synchrotron desert. So one of the reasons why I'm quite interested in bringing these type of capabilities here to Georgia and Atlanta, Georgia Tech, is that regionally we are starved of this kind of facility. All right, so what can we do? So as I said, we need kind of a broader spectrum of X-rays. Now it turns out that we do have a broad spectrum of X-rays that we're generating all the time in our lab sources. It's just that we are not utilizing them properly. So one of the ways in which we generate X-rays in the lab all the time is um, is through these um, X-ray tubes that generate your characteristic X-rays necessary for X-ray diffraction, for example, or XPS. But it also includes this broad spectrum that is thrown out, and the reason it's thrown out is because we want a characteristic X-ray photon for our analysis for something like diffraction. So when you do X-ray diffraction, you're using copper K alpha, the family, typically, and so that copper K alpha emission for X-ray diffraction is a very specific energy. But in order to generate that copper K alpha, you're also generating a whole plume of other X-ray photons that your instrument is intentionally eliminating. So the redesign or the rethinking that you have to allow for is that we are now going to focus on the rest of the X-ray envelope and see whether we can raise the intensity of that envelope higher to be competitive enough with synchrotron sources. It's never going to be competitive in a side-by-side analysis. You're not going to get that many photons, but you can get to the point where it's feasible to do these kind of experiments in the lab, albeit with longer acquisition times. So what I'm showing here is that, for example, if you use an indium target or a silver target, you see this broad spectrum of X-rays that you're generating. Normally, all of this is thrown out, and what we use are these characteristic emissions. But if we change our thinking, we can use the broad spectrum and basically avoid the characteristic emission regions in order to use a kind of a broad high intensity spectrum. So here's a table now of comparing what we might possibly get to with lab-based sources in terms of intensity, sort of a apples to apples comparison with the synchrotron beamline type of capabilities. And you can see that in the best cases that we can imagine for our lab-based ones, the green dots here, we are still going to be several orders of magnitude shy of what we get at a synchrotron, but that may just be enough. I should just point out that this particular one here is so-called XLM metal jet X-ray source, which we don't have at Georgia Tech currently, but it is one of the types of X-ray sources that we are thinking about for the future. So at Georgia Tech, we currently have a Bremsstrahlung X-ray. So Bremsstrahlung is this broad X-ray range. This Bremsstrahlung based X-ray based instrument, which allows us by some, with a clever design, allows us to do both X-ray absorption and emission. So essentially, the sample detector and X-ray source, um, as well as the monoparameter crystal, essentially all sit on the arc on the circumference of a so-called Rowland circle, and by doing so, we are able to take out emerging um, X-rays from either the sample or from the X-ray tube, and do Bragg diffraction using the crystal while also refocusing them back to an image point that images the source back. So in other words, we recollect the large solid angle of emission that's hitting the crystal. So in doing that, we can essentially, by changing the angle between the crystal, the source, and the detector, we can change the energy of the X-rays reaching the detector. So if we do want to do X-ray absorption, we use an X-ray tube, and the polychromatic X-rays coming out from the X-ray tube are then refocused, but also energy selected by using the particular angle that the crystal is sitting at. And that particular X-ray energy then is passing through your sample and reaching the detector. So as we rotate the crystal, we are able to scan in energy and do an X-ray absorption measurement. Similarly, if we irradiate the sample directly with an X-ray source from the outside first, and then look at all the X-ray emissions coming out of your sample, we can use that same crystal to energy select the emissions coming from your sample, and then we can do a high energy resolution X-ray emission spectroscopy. So that's basically what we can do here in this instrument that's pictured on the left. Using this, we can essentially get analytical measurements from this swath of the periodic table currently. But you will notice that we cannot do X-ray absorption of everything, but X-ray emission is possible for a very large swath of elements. And the reason why we cannot reach all the elements with X-ray absorption has to do with the geometric limits and the particular types of crystals that we currently have. When you could do these kind of experiments, the comparison to beamline, that is a synchrotron beamline data, is quite good, albeit with a lot more time needed to get similar quality data. So essentially, what the point of this is that there's no embedded artifact that is coming from the lab-based instrument. They're giving you very similar information to the beamline, and a simple rule of thumb would be that it takes about 6 or 7 times more, in the concentrated sample cases, 6 to 7 times more than in terms of time to get similar type of quality as what you'd get at a bending magnet beamline. We've done this. We've used this kind of work to do study of battery chemistry in a real battery under operating conditions, and so here is kind of a large array of data. Of course, we're so zoomed out you cannot see what the details of what is happening. But if you look at the differential measurements here, you can see that there is a lot of differential in the differential scale. You can see that there's a lot of changes that are being picked up. And so those changes can be used for tracking the state of charge of the battery. And so one of the first studies we did was to benchmark X-ray emission as an analytical tool for following the battery chemistry of a battery. So here's the extent of dilithiation in 4 different battery chemistry, and we can see the extent of dilithiation can be followed either by X-ray absorption, which is already known, and a lot has been done, but also by X-ray emission, which is a new technique, you might say, for battery characteristic batteries. So just to show you kind of the level of detail that we can get from X-ray absorption that is at our instrument, and what it tells us. Here's the first charge versus the second charge in LFP, or lithium iron phosphate materials, and you can see that there's quite a big difference between the first charge set of data and the second charge set of data. Second charged set of data looks prettier. Why does it look prettier? Because there are these pinch points in the data. These pinch points are the so-called isosbestic points, telling us that there's a single reaction path happening. All the side reactions have completed. In the first cycle, because there's a bunch of separate reactions happening, those pinch points cannot manifest, and so it looks a bit more let's say haphazard. The data looks more haphazard, but it basically gets cleaned up by the second cycle. So that mere fact that we don't get the isosbestic points in the first cycle tells us that all these side reactions are happening. If we get the isosbestic points in the second cycle, it means that majority of them have already completed, to the extent that we are getting essentially a single reaction from the second cycle on. So this kind of analysis is possible. Uh, this is now, I'm showing a quickly some data from the Losego group. This is work in collaboration with us. They are interested in these so-called polymers with intrinsic microporosity that can be hosts for inorganic particles to adhere to them, to interface with them. So they use a very special technique called vapor infiltration, by which they are doing something akin to ALD, but the ALD is now of inorganic materials onto um, organic interface, organic surfaces, internal organic surfaces. So think close analogy would be a moth a system, like growing inorganic materials inside of the walls of a moth. So one of the things that we were able to do in using this instrument is we were able to show that that there's kind of a polymerization, a mini polymerization type of reaction that's happening in the zinc-centered inorganic materials as they are growing onto and linking to the polymer matrix. But this is from zinc. Zinc is something we can do with our instrument that we currently have. But here's another work that we are collaborating it with. But for this work, it's the same type of reaction, but for aluminum based oxyhydroxide structures that are growing on PIMS. But aluminum happens to be at an energy, if you want to interrogate aluminum, it happens to be at an energy range that we cannot access with our current instrument. And because we can't access with our current instrument, we had to go to synchrotron, and this is synchrotron-based data that is showing a transition between Gibbsite and conundrum phases of this alumina. So what we would like to do, looking into the future, is to bring kind of the soft and tender capability, X-ray capability of the type that we can do at the hard X-ray energy range to Georgia Tech. So that's kind of the segue to where we go next. And what I want to talk about in the next couple of slides is that we have this a vision to bring the soft X-ray capability. So now if you look at the periodic table, we will be covering, if we can get this capability, the first few rows of the periodic table. And in so doing, we can bring in the entire soft matter community, which that soft matter community essentially has been excluded by our current capability. So here's an instrument that is now currently commercially available. Here's a picture of the instrument itself and some schematic drawing of how it works. And in this case, the X-ray is generated by irradiating a gas with a laser, and so you then generate a plasma, and without getting into the physics of all of that, you generate a broad spectrum, but on the soft X-ray inching towards the tender X-ray region, that part of the spectrum. And so that's perfect for what we need. And so we use that X-ray source then to do the kind of experiments that I've been describing previously. So here's a side-by-side comparison of beamline data and the lab acquired data for using this type of an instrument, and you can see that they're very comparable. The one on the left is the lab acquired one. You can see it's slightly noisier than the beamline one, but if you're interested in the features that you're going to be used for an analysis, the features match very well with beamline data. we are not the only ones, like at Georgia Tech, who are thinking. I mean, Georgia Tech is not the only place where people are thinking about this kind of bringing beamline level of capability to a lab scale. So here's an example of Ashley Butzek's lab in University of Michigan, and she is focused very much on the diffraction and diffraction-based microscopy and CT, that is tomography-based work, but trying to replicate the kind of capabilities that you have at a beamline using X-ray sources. And they've basically this is a picture of their lab beamline, and they're basically trying to do this with that Excelum source that I had pointed to before. So this is another direction in which we can go. We can and complement the spectroscopy I've been talking about with imaging and diffraction.